Okay, let's start. Shibor, go ahead.
Okay, so let's get started. So today I'm going to continue the topic of operator learning, and today I'm going to talk about another branch of work about the operator learning called DeepNet, and I'm also going to talk about the physics informed operator learning. And this is the main reference of today's presentation. I will mainly focus on these two papers, and I will just summarize these two papers in just one or two slides because their contributions are very trivial. So this is the agenda of today's presentation. First, I will, since the last time it has been several weeks after last presentation. First, I will give a quick review of what is the operator learning and what's the motivation of the DeepNet and their methods and their the extensions, the physics informed extensions of the DeepNet, and the comparisons between DeepNet and neural operator. Then I will the last I will introduce the physics informed neural operator at the end of today's presentation. So what is the operator learning? So if you didn't attend previous presentation, my previous presentation, so previously, we want to learn the function, the mapping from function, the mapping of a real space, for example, RD to Rm, for example. This is what we could use a standard neural network to do this, and then your input space is D, and your output space is M. Now we want the operator learning is to learn a function, the mapping from a function space to a function, from functions to functions. Instead of you have discretized input space, now you will have a continuous input and output space. That's basically what the operator learning does. And in the previous presentation, I mainly focus on the work of the neural operator. The neural operator is like the structure of the neural operator is like P and V0 to VL and Q, and the P is a lifting. This is your input function, and this is your target function, the output function. So for the neural operator, we first lift the input space into a very high dimensional space, and the intermediate layers are the neural operators, the building blocks of the neural operators. They're using the projection matrix to downsampling the hidden space to your output space U, and each component in between is a neural operator, and the neural operator, for example, the else neural operator is W WV L-1 plus a K X KVY times dy. Sorry. This is KXY dy and dy. And the key idea of the neural operator is this integral, and we have already seen that there are a lot of ways to approximate this integral. You can use a graph neural network, and that their latest, or you can use the low rank approximation, and their latest work is using a Fourier transform to approximate this integral. That's a quick summary, quick introduction to the operator learning. So today we are going to talk about another work called DeepNet. So the motivation of the DeepNet is, so in the machine learning class, we have already know that the neural network can be used to approximate any continuous function to arbitrary accuracy if we don't put any constraints on the height and depth and width. So that's a very famous conclusion. But there is another conclusion that is a single hidden layer neural network can approximate accurately any nonlinear continuous functional. A functional is a mapping from a function to a function value or a nonlinear operator. That's basically how the DeepNet is. This is the main theory how the DeepNet is derived. So now we have we want to learn. This is your input function, and we want to learn operator that maps the input function to the value of the output function. So then your model is taking the discretized of the input function, also the inputs of the output function, and predict the values of the value of the output function at y. Any questions so far? So this is a very simple framework.
You should clarify the input function. That should be some discretized version.
Yeah.
Yeah,
right.
Inputs.
Yeah. So we want to ideally learn a function to a function, continuous function to a continuous function, but clearly in realistic we cannot do that. So we still assume that the input functions that are discretized, and also the output functions are discretized. And from this figure, you can see the main difference between the neural operator and the DeepNet is the neural operator tries to take the input function and the output discretized output function like this. But the DeepNet tries to take the input for discretized input function, also with the input values of the output function, and predict the output function value here. So that's the main difference. They formulate the training examples. So in the neural operator, you have a pair of functions, and in DeepNet, you have to expand the output functions into multiple copies of the input function plus the inputs of the output functions, also the output function value. So basically, there will be a tuple. This is your discretized input function, and where is the output function is evaluated, and what is the ground truth output function values. So that's the main difference between the DeepNet and the neural operator.
Sorry, a quick question. So in the figures, is the x and y, are they in the same function domain? I mean, the y is in the... Yeah.
That's a very good question, actually. So I will talk about later. So neural operator can only handle that x, y are in the same function space. And but DeepNet doesn't have such restrictions.
So for example, the y here is equal to some Euclidean d-dimensional Euclidean. However, you say x here, it now has to be there some variable in the d-dimensional Euclidean space, right?
You mean the dimensions or the
the dimension,
the domain?
Yeah,
the dimension doesn't have. Yeah, the dimension doesn't have to be same. So even for a neural operator, the dimension doesn't have to be the same.
I see.
Yeah, a good example is so if you want to design or solve the aerodynamics. So if you can think that this is a airplane, and you have air flow. If your input function is defined on this domain, and your output and your interest domain is around this domain, so clearly the input functions, the domain of the input functions and the output function are not the same. So the neural operator cannot handle this kind of scenario, but DeepNet can.
Yeah, I see. Thank you.
So I mean, in a neural operator, you assume the target function and input function share the same input domain.
Yeah, right. So in the example, so for the Navier-Stokes, the input and output function domains are the same.
Okay.
Yeah, that's that is very good question actually. Yeah. Thanks. And any other questions about this?
Yeah. Hi. Hello.
Yeah, sure. Go ahead.
I'm very curious about the x1 to xm and ym. So there, is there any mapping between the xi and the y? I didn't understand. I didn't get.
No, there isn't any mappings directly from the inputs to inputs. That's just how you discretize the function space.
Okay, so okay, so why? Okay, so y is the input for the capital GU function?
Correct. That's the target
okay.
function, the inputs of the target function. I know the notation is kind of confusing. They should use Z or C something.
Okay, yeah, I see. Thank you.
Okay.
Yeah. So I got a question. I feel why if you define your convolutional kernel to, you have an input to your two convolution, you have two inputs to the convolution kernel, right? You just need to specify Ix in one domain and Y in another domain. There's not such kind of restriction.
What do you mean?
If you look at the Fourier net,
yeah,
the updates you just wrote in the previous slide. Yeah, if I define my kernel, my convolution kernel, you have two inputs, right? Y belongs to one domain, Ix belongs to another domain. You just change the domain. Why?
X and Y are in the same domain. They have to be
X and Y be in the same domain. If you get V0, if you get in your V0, you get rid of this W times VL minus 1, whatever. You get rid of this linear term, and then in your convolution kernel, your very first convolution kernel, you just define your x to be the domain of the target function. Then in the following sequential transformations, you just make the two inputs of convolution kernel to be the same domain. You can change the domain.
Yeah, right.
Like x can be in R1, but y can be in R2. Right? So
If I write down as this way,
unless there is some restriction for using Fourier transform, inverse transform to compute this convolution. Otherwise, from the formulation itself, I can't see why the input domain, the domain for the input function, output function must be the same.
if x and y are not in the same domain, so how do we define this? So
Okay.
because if you
want key x and y to be stationary.
Yeah, so if you want to apply the faster Fourier transform, you have to assume your kernel is a stationary kernel. So if x and y are not the same, so how do we define this properly?
Then that's just because of this Fourier transform trick.
Hmm.
It's not because of the model.
Yeah, right. Okay.
I know. I think there can be other tricks to do that. It's not necessary to be stick to the stationary assumption.
Yeah. Okay. Yeah. Let's move forward. So basically, that's just the DeepNet, and let's talk about where they derived. And so this is the second universal approximation theorem I mentioned at the beginning of this presentation. So the universal approximation theorem for operator learning is, so if you have a function which is non-polynomial function, and X is a Banach space, and you have a compact space on the input and outputs, and V defines V is represent as no, G is a nonlinear operator that maps a compact space in K1 to K2. Then for any epsilon arrow, there exists such constant that your neural operator learning, your operator is your learning arrow is bounded by epsilon. So that's the this is the is for one hidden layer neural network. And if you think it as a neural network, the sigma is the activation function, and C is the weights, and sigma is also activation function. Then you can see that we can naturally derive the neural operator, but no, the DeepNet. This part is the branch net, and this is the trunk net. that's the theory background of the DeepNet.
And this is just the one. It only uses one hidden layer for.
It's just for one. Yeah, this Process theorem is for just one hidden layer neural network. So, given this universal approximation theorem, then we can define the neural DeepNet. So DeepNet assume you have pairs of input and output functions, and DeepNet they claim that it is very flexible because the only requirement for training is that you have to align the discretizations of the input space. Like you have to align the discretizations, but there isn't any requirement for how to discretize the output functions. You can discretize anywhere or just at a single point. So that's how you formulate the training examples of the DeepNet. And a straightforward model is just using a neural network that takes the inputs, the values of the input functions, also with the inputs of the output functions, and output the value of the output functions where y is evaluated. But by doing this, there are two clear disadvantages. So the first one is, so if we concatenate the values of the input functions and the inputs of the output functions, then it will lose the input structure, and this cannot be used to handle high-dimensional output space also.
Shibo, can you look at the theory again? I want to see where the discretized function come from.
Come from here.
The input to the branch net.
Yeah, right.
Okay, it just says that there are m input function evaluations. So that's the input to the branch net plus the bus. Okay.
Yeah. And then this is your trunk net. So the trunk net takes the inputs of the output functions, and the branch net takes the outputs of the input functions. And this is the bias of the branch net, and this is the bias of the trunk net. So that's so then by combining the difficulties of modeling concatenate the inputs and the outputs inputs, and also the universal approximation theory. So the key idea of the DeepNet is to handle the inputs of the output functions and the outputs of the input functions separately by using a branch net and a trunk net. So they developed two variants of DeepNet. One is called stacked DeepNet, and the one is unstacked DeepNet. And so the stacked DeepNet has has several branch nets and one trunk net, and the unstacked DeepNet has only one branch net and just one trunk net. And after you map the outputs of the input functions using the branch nets or just one single branch net to a p-dimensional space, and you're using the trunk net, map the inputs of the output functions also into a p-dimensional space. And then if you denote this p nodes as the vector, and this is also a vector t, then the outputs of the DeepNet is just the inner product of those two vectors. this is B transpose T. And also you can add bias if you want. Any questions about this structure? It's quite straightforward.
Yeah, I have a question. So here for the so for the capital G U Y, actually that's a function of a function. So here it uses the dot product to.
What do you mean? It's a function of function. It represents the output function.
Yes, yeah. It's an output function. So what I mean here is that so firstly it uses the branch net to learn the UX. So that's one function, and then it uses the branch net and the trunk net together to learn the GUY.
Yeah.
So I'm very curious why it uses the dot product to represent the function. So is there any intuition here why it doesn't use the other way?
It's because it's simple. That's my guess.
Okay.
And because the first observation is that the GUI has to be a scalar. So what's the scalar? Most easy way to come up a scalar? It's the inner product, right? So that's my guess.
Okay. I remember it for pin. So the architecture is different from the DeepNet, and I remember it also. It has one network, and then with that network, it calculates some partial derivative and then gets a loss. So for that, it seemed embed more physical information there, and for the current DONet.
I will talk about I will talk about the physics informed DeepNet later in this presentation.
Okay.
So the metaphor here is you can think the DeepNet as a model that generally learns the functions mapping from functions to functions. So you can think it as a neural network in general. And then we will talk about the physical informed DeepNet, which will be the PINS, physical informed neural network. So that's the comparison, parallel comparison. And then another thing, I think another thing here, this is the questions I have all the time across reading those papers. So I think this is just my personal opinion. I think DeepNet it's not exactly learn functions to functions. To me, it's like learning a function to a particular output of a function. So no, I don't know, just my personal opinion. So the problem setting.
Yeah, I think the dot product here is just the fulfillment of the theory. If you take a look at theory.
Oh yeah, that's fulfillment of theory. So this is this one. Yeah, thank you.
And the structure looks similar to attention.
Yes, right. Yeah.
And what if the operator, the value of operator depends on X? I mean, for some function, the real operator.
Yeah. They you can also Well, then the remaining are just the engineering issue. Then you can then you have to I think in their journal paper, then you can also put your feed your X into the branch net
Okay.
if your operator is depending on the X also. That's a good question.
If the operator depends on X, what do you mean?
Well, it means if the real operator is some derivatives terms plus some terms with related to X, then this structure may not capture the real underlying operator because they only depends on the value of the output of the function u here. They did take X into consideration in their structure.
Then X will be the Y, will be fed to the Y.
Y is a value of u, I think.
Yeah, in John's case, the X is imputed into the branch net, not the trunk net.
Yeah, they don't know they don't know the input of Y here.
So I mean, your operator depends on both U and X.
Yeah, it could happen if you have I think for all some of the PD system, if you have multiple derivative terms, then your integral operator also depends on where your input function is evaluated.
Usually it is about some integration about U. So if even it is depends on X, you should say it depends on integration over X. That's why this is a operator. Your input is functional U, and through some operation going through the X has been marginalized out.
Yeah, I cannot come up with a concrete example, but this issue I think also mentioned in the neural operator learning. So for example, if you're then this kind of information is designed into the kernels. So for example, so we use this simple kernel, which is X and Y are both the output function or input function values, but you can also design, well, in their paper you can also design something like A, which is then your input is not X and Y, C, for example, and then your Z, which is the true input. So this information is incorporated into the kernel function. But I think this problem does exist in the PDE operator learning. The operator could, depending on the inputs also.
Actually, if your operator, I mean, if you want to compute the operator, if the solution is some integration with respect to U and over X, you shouldn't realize it depends on X because it marginalizes over the whole X. Unless your final result is also dependent on a particular X, which is assumed to be Y here. Like for example, if you have I can write anything. For example, if an ODE, right? If you have an ODE, your input function is yourself and also the t itself, right? When you solve that, you're going to integrate over not only the time derivative, which is function of your function itself, and also the input t. But finally, you still got your function.
Yeah, I understand.
Yeah,
I understand.
The marginalization you shouldn't view it as dependent on.
What if we are not learning a integral operator, we're learning something else?
If you learn derivative, then y should be your input. Although for the derivative, like for example, the operator is just the first order derivative, like your g equals to u prime x, right? So of course you don't need the whole u vector, the whole u function to get it. But conceptually, it still depends on u itself, and you want to know at which particular point what's the derivative value. That should be the y.
What if they for the function u, they have multiple same values for different locations with different derivatives?
Yeah, you can just discretize it. The idea is that you're gonna assume the discrete version through some interpolation, you can recover the original function information.
Yeah.
And all your other properties we mentioned, if they have the same value at different locations and they have the same derivatives at different locations, can all be reflected in this discretized long vector. This is like if you want to compute the marginal distribution. Like you have a p of xy, you want to compute p of y, you shouldn't say your marginal. Your p of y is dependent on x. Because when you calculate, you have marginalized out x. Although this marginalization in every particular step, like infinitesimal area, of course it depends on a particular x. But they want to learn the mapping from some particular value y to the result after marginalization. I mean, integrate all the x.
Okay.
What if we also have some boundary conditions or initial conditions? Then we are not doing the integral over.
If there is a boundary and the boundary initial conditions, which also determines the mapping, then this is not sufficient. You have to fit the boundary conditions or initial conditions into this dipole net as well.
But we can compute.
Or if for example, if the PDE itself is only determined by the initial conditions, boundary conditions, then your input should be the initial conditions, boundary conditions. So for some PDE, like the initial conditions should be u.
Okay.
But if it also determine the PD parameters like viscosity in the Burgers equation, well, you gotta have an additional input.
Okay. Yeah. And yeah, sure.
Sorry, I have a very naive question. So here for the input, actually the input is the interpolation. I think that's x1 to xm. So why for the input it's not the x1 to xm instead actually that's the uxi to the branch.
Yeah, because
could you give an example? So for example, give an example of the ODE to show what's the X, what's the U, and what's the capital G there. Yeah, because I'm a little confused about the problem itself.
So for example, if you have a PDE system, no, not PDE system, ODE system, like this one, and usually the dynamics we know, right? And we know what's the initial condition of this ODE system, that's not S0. And we want to learn the mappings from UT to ST. The GU here is then it's an integral operator.
Oh, I see.
Right? Yeah. It's basically your GU is S0 plus U, for example, UX, your integral over the UT times DT. Then your no, this should be Y. This is your GUY.
Shibuya, you can write your dynamics, I mean the derivative to be U. Oh yeah. It's a function of U. It's function of U. Yeah, it's good. Yeah, it's good.
So it's just this is a simple example. No, I don't know any other complex PDE example. I'm not really familiar with PDE, but this is ODE example. And any other questions about the structures of DeepNet?
Oh, my in these examples, the U can also be S, right? To train the mapping from S to U.
What do you mean U can be S? S is the integral of U.
Oh, yeah, but it, I mean, in practice, if we can get the value of S, we are curious about some other values that generated by doing some operation over S.
Then you are learning a differential operator, not the integral operator.
So it could be the case, right?
Yeah, it could be the case.
Okay.
Any other questions? So then the remaining of this there. Oh yeah, they make this example. So this is just a theoretical analysis of how many M we need. So basically for M discretizations of the input space, and you discretize the input space uniformly between A and B. And there is some mapping restrictions of what is your I think in their notations is the operator. There are some restrictions, mathematical restriction on G. Then the number, this is the, if you use M sensors, then your arrow could be bounded by a constant. So this is just a theoretical analysis of how many discretizations you need at the input space. And then this is the experiment. This is their they made experiment settings. They made examples of the linear ODE, nonlinear ODE, and pendulum ODE and diffusion reaction ODE. This is where how they generate it. Is that they generate the functions from a Gaussian random field with this length scale of the Gaussian random field, and this is this is the input sensors, and this is the training examples, and this is the test examples, and this is the number of iterations. They also test on different structures on the ODE. Well, based on that, you can see that training the DeepNet is not cheap. You can see for a simple linear ODE case with just 100 sensors, and they train their DeepNet 50,000 iterations, and for this practical PDE example, they trained actually 500,000 iterations. So that's train the DeepNet is quite expensive. Yeah, this is the structures of their DeepNet.
So they always use ADAM? Did they use LBFTS?
No, they always use ADAM in this picture.
Okay.
And first they do their DeepNet experiment on, I think, yeah, this is a linear case, and they just compare the DeepNet with a vanilla neural network. And this is, you can see this the training and testing errors. And they also vary some hyperparameters. And this is the FNN, and this is the DeepNet. And the FNN can achieve the 10 to the negative 4 MSE at the best. And the DeepNet could achieve 10 to the negative 5 at the best. So yeah, that's the linear ODE experiment. Yeah, any questions about this? Yeah, then I will just jump to the physical informed DeepNet, which is by UPenn. The key idea about the DeepNet, why the DeepNet is problematic, is it tries to infer a system laws, but it doesn't incorporate any physical laws. But actually, those physical laws partially or totally known to us. So by incorporating those physical laws, we can reduce the number of training examples dramatically. And actually, for some simple examples for this linear ODE example, they can achieve 0 training examples. So this example, they show why DeepNet failed. So if you want to learn this linear ODE, and you are basically trying to learn integral operator, and so basically, if you don't have incorporated any physical knowledge, and you can see that the dynamics learned is problematic, and yeah, that's simply minimizing the data loss is problematic. So just using
why is it problematic?
Yeah, because it doesn't fit it very well. I think it's I don't quite understand. I think this part is it's not very good. We're trying to learn S, but actually S learns pretty well. And then you differentiate S, and you get something like this. The stage shape is not perfectly. This is the DeepNet, where the DeepNet learns. And in the paper, they said, so okay, this because this could be, you could say that this is because the ReLU function is used. But if you replace it with a smooth tanh function, it's get worse. So
But they learn S is learned well, right?
Yeah.
They just that means the S actually is not a good surrogate of the solution because when they take the derivative, they cannot recover U. Is what they're saying?
Yeah, that's their claimant. So visually, we can see that the learn S is good, but if we take the derivative, it's not good.
Yeah, it's not necessary, right? Because our goal is to not S.
Yeah, but visually, I don't know. This is their justification.
Okay.
Well, in their paper, they show after, I think in the experiment part, by incorporating the physical laws, you can learn it perfectly in their experiment.
Yeah, because they add additional constraint.
Yeah. Yeah, the key idea is identical to PINN. If you are very familiar, PINN is basically, so this is the L2 loss, or you can call it data loss. And now we add a physical loss, and the physical loss is you have to put some physical constraint. This is the N is defined as the physical loss of your PDE system. By adding this, and this term can be computed using the auto differentiation, and also you can, of course, if I think this figure is yeah, but yeah. So the basic idea is that this is the vanilla DeepNet, and you have this function, and you take some derivative to force your learn operator to satisfy some constraints, physical constraint, and you can also similarly compute some boundary and the initial condition, and then you added them together. This is your total. For here, you have a data loss, and this is your physical loss, and they put them together and using Adam to optimize this, and then you can learn a better parameters of the operator. So that's basically just identical to the key idea of the PNN.
So said that they can even get rid of data loss and the result is also good.
Yeah, for example, for this example, if you know U, right? If U is known, then we don't need the operator, the L2 loss. We can just using force data. It satisfies the physical constraint. We don't use any training examples at all. Any questions about this physical informed DeepNet? Yeah, that's yeah, they made a very simple example. So it's a linear ODE, and that is your parameter. For this example, you don't need the L2 loss. You can just impose the physical loss, and you can achieve a very good results. But to me, this is kind of cheat. If you have this simple ODE system, and the dynamics is known, you basically just learn the dynamics is not magic or anything fancy.
Well, how many samples do they use for the training?
1,000. No, this I don't know. They use 10,000. For this example, they use 0.
Oh.
Yeah, 0 training examples. But I don't know how many calculation examples they used. But they use actual 0 training examples for data loss evaluation. But I don't know how much.
The test examples are 100. What do they mean? 10H activations over 1,000 examples in the test data set.
they sample another 1000 UH and they evaluate the DeepNet. They are physically informed DeepNet. That's how they evaluate it.
So nothing is fed to the branch net, right? If they use 0 training points.
No, I don't think so.
For the collocation points, I mean, you still need to sample a lot of functions, input functions, and feed them to the branch net, and then calculate derivatives at different collocation points to construct the residue term. It's kind of like an upgraded version of PIN. Your PIN, the PIN network has the input, I mean, of the solution function, right? But now the solution function depends not only the input location, but also some input function. So that means you have to sample a bunch of input functions and their locations to construct the residue term.
Yeah, there are still inputs to the branch net because you need to sample some functions, but you don't need to evaluate on the output functions anymore. You need to don't use the random CUDA solver to solve this as to train the DeepNet. That's the idea.
Do they have more complex experiments?
Yeah, they have burgers. This is the burgers, and that they also derive the physical loss on the burgers.
What's the input function to the burgers? It's just software?
The input function is
it's the initial condition.
Yeah.
Equation 4.11.
This one, right? This is a sample from a Gaussian random field. This is your inputs, which is the initial condition. And
can you go back to the linear case?
this one.
Yes, so the physics. So for the collocation points, the physics loss term here. Oh, so the collocation points are all UI here, right?
Yeah.
And the Y is the same.
Y
as U.
I mean this Y?
I mean the physics term, physics loss term. Yeah.
Yeah, this term and the Y. You don't need to. You don't need. It doesn't have to be the same. So the first procedure is you need to sample UX, like for example from a GP prior, and then you have a bunch of U's. For example, this is U1, U2, U3, and then you discretize those. You have a n by m matrix. Then you can then this is your inputs to the branch net, and then you have then you just randomly sample. I think you can just randomly, for this example, you can just randomly sample some Y's, and then this is your trunk net input, and then you will have a G, U, Y, right? Then you can just using auto differentiation to compute this term, and this is your physical law. You have a closed computational graph here. You don't need to evaluate any ground truth GUY in this
Sure.
example?
Their notation is kind of confusing because they also make y equals to xj. The gradient is evaluated at y equals to xj.
Oh yeah. Let me think. I think it just y.
Maybe y equals to uxj.
No, it should be xj. Because you can.
It just means if you take the derivative of x at xj, it should be the same as uxj. Right, just to obey the equation.
Yeah.
Okay.
It's just uxj. Each point.
Because in the previous slides, J takes two inputs, U and Y. They are in the same function space. Not the inputs, not the input space of the function. So they make y equals to xj. Xj should be the input of the function, not the function value itself.
Can I see it again, John?
I mean here I think the correct notation should be the derivative of G U I Y with over dxj evaluated as one y equals to uxj. Because y and u should be some values in the same space.
No. Y is the input location of S. So look at the ODE. So d of S x over dx, x here corresponds to y there.
Oh, so they changed the notation for
They changed the
D
notation
here.
for the input location to S.
Okay.
They just want to obey the equation.
Okay.
Yeah, great. Go ahead.
So yeah, so I would like to ask a very simple question. So when for the example, the Gaussian, for the UX function, so you give some example U1, U2, U3, and then for each UI, it seems like a vector. So I'd like to know. So what's the UI? What's the mathematical formulation for the UI?
It could be anything. It could be anything. Just for simplicity, we can sample each UI from a Gaussian process prior. So you sample could be something, right? So this is UX.
Oh, okay. So for the UX, there is no. So at first I thought, you know some equation about the UX. So somehow like the UX is equal to X at the X square, something like that. So it's unnecessary to know the.
No, it's not. It's not unnecessary. So if you do this sample from a Gaussian prior, we don't know the closed form of each UI, right?
Oh, okay, I see.
Or we know. I don't know if you sample from a prior.
So if is that important to choose the prior for the UX?
No, there is an UU is given in realistic. It's will just give you a discretization of the functions. It's given to you.
Okay.
Yeah. So for this, U is not learned. So in practice, U is given. But for this example, we want to generate functions, input functions with the convenient way is to sample the functions from a Gaussian process.
Oh, okay, I see.
Yeah. So this is their progress equation, and this is the results. They show the absolute arrow here. I think this is the DeepNet. This is their physical informed DeepNet. The arrow is smaller. So any questions about the physical informed DeepNet? So if you remember, last time I introduced a neural operator, and in their journal paper, they said DeepNet is kind of a special case of neural operator if you choose the kernel function very carefully. And they also compared the DeepNet on two simple examples, and they improved the DeepNet like several magnitude, and clearly the authors of DeepNet is not very about their comparisons, and that they make a journal summation that compare the DeepNet and the FNO more systematically. So then we will talk about the DeepNet and the FNO. In not FNO, well, they said FNO. So in their journal paper, they make several statements. So they said they introduce extra features into the trunk and branch net, and now the DeepNet can handle some hard boundary and initial constraints. And they also develop pod DeepNet, and they also re-implement the DeepNet with a more efficient way, and they extend the DeepNet can handle the multiple outputs. I remember that the previous one restrictions about the DeepNet is the GUI has to be a scalar, but now they can handle it into it could be RD. And two problems with the Fourier neural operator is so first, it cannot mapping from different domains. So they make a modification for the Fourier neural operator called DFNO plus that can handle the nonlinear mappings on different domains. And they also, another problem with the Fourier neural operator is that it cannot handle complex input domains. For example, if you have an irregular input function domain and you have a hole in the middle of it, the FNO cannot do that. And so they modify propose another modifications of our FNO called GFNO that handle the complex geometry of the input functions. And they compare the FNO and the DeepNet on 16 experiments, PDE functions. And the most, I don't think there is any concrete contributions in their statements. I think most of them are just engineering tricks, and their extensions about the FNO and the GFNO is kind of trivial, and we will see later. So the first development they made is so instead of using the raw function values of the input functions, we can do some feature expansions, and we can use the Fourier features as the input of the branch net. The good thing about this, if we know that the output functions is a periodic functions, we can use that knowledge. We transfer the values of the input functions into the Fourier features. Then it could be help with learning the output functions. That's
So Cassie is what? Is a branch net or?
Yeah, they use another notations here. Cassie is the inputs of the input functions.
Input of the input is the x1, x2 to xm?
No, it's the value. It's the outputs of the input functions. Sorry about that.
But how does it relate to these Fourier features?
Well, if previously you for each ux1 you have a you just use this input, then you can expand it into long Fourier features and concatenate all those Fourier features. Previously, you use a
FFT to U?
Not FFT. It's just the Fourier features, not FFT. Yeah. Previously, you have ux1 and the ux2. Now, I use this as input. ux1 cosine, ux1 cosine, sine, ux1.
Oh, they do some feature transformation.
Yeah, right. Cosine ux2, and so on. Basically, by doing this, you will have a very long input space.
Okay.
But it will help with the learning of the output function. That's one thing, the feature expansion.
Okay.
And you can also do, now you can also put some constraints, because in PDE learning, you will always have some boundary or initial conditions. Their way just to put a term here, and the force, the GV, the operator to learn the boundary conditions, or this the tau D is the boundary of the input domain. That this is boundary conditions, and yeah, and we can put some functions here, and if Cassie is residue at the input space, then we let the L Cassie is equal to 0. Otherwise, we put something else, which I can think usually it's just 1. But if you choose some other values, you can think it as a regularizer or something. And if you do the transform, then it will handle this set. It will handle periodical boundary conditions. So this is for Dirichlet boundary conditions. And then if you do the Fourier features, then they will handle the periodical boundary conditions.
It said that enforcing Dirichlet boundary conditions in neural networks have been widely used in pins, given the reference 13. What's that reference? I'm curious to know.
Okay. It's this paper, physically informed neural network with hard constraints for inverse design.
Okay. Okay.
Yeah.
Yeah, Madison, you might need to check this reference. This looks like they're
Yeah, I've read through that one.
yeah, strong pin.
Mhm.
Okay.
And this is previously we do the inner product, and what they propose to handle. What if you have this is belongs to RD, for example, then you just need to group those P nodes into D groups and do the inner product group by group. Then we will have a D-dimensional outputs. So, any questions about this? This is straightforward.
Well, when they do the comparison, they always compare with this expanded with DeepNet after feature expansion with the Fourier net.
It varies from experiments to experiments.
Okay.
Yeah, for some experiment, maybe you need to do the feature expansions. For other experiments, you don't need to do the feature expansions. They just want to introduce as more engineering tricks as possible here. Yeah. And you can also, instead of expand the input features, you can also decompose the input features with this pod called orthogonal decomposition. Make the input features more small, and use that as the inputs of the branch net. No, the trunk net. Sorry, this method. So you see that the problem with pin is that what if your output functions is has 1 million discretizations, and this will for each U you will have 1 million training examples. That's very expensive. Then you can do the pod or PCA on this white space, and then you use that as the input to the trunk net.
So here at phi 0 to phi k are the
PCA modes.
exactly the basis.
Yeah.
And then your trunk net should be the output dimension of your trunk net should be the number of the PCA bases.
Yeah. So if you have a Navier-Stokes equation, the output space could be 1 million. But by doing the PCA first, they could be shrink to 10 or 20 something.
Yeah, this is essentially PCAGP, right?
Yes, right.
This is PCAGP,
yeah.
Except that now your input of the coefficient becomes the discretized function B.
Yeah.
Not the parameters we used before.
Now they compare to Fourier neural operator, and this is just some slides from last time. So this is the model of the Fourier neural operator. You have the input function, this is your output functions, and then you have Fourier layer. Each Fourier layer is basically solving the integral, the computation of the integral issue in the Fourier space. This is the nonlinear activation function. This is the inverse Fourier transform. This is the Fourier transform of the kernel. This is the parameter we need to learn. And then this is the Fourier transform from the previous layer. And you can also have some local transformations of the inputs. Basically, this is mimic the behavior of a traditional conventional neural network. Besides, you need to do these operations on a continuous space. And the Fourier features have one good thing about the Fourier. There are two advantages about the Fourier neural operator. First, the Fourier features are global. Unlike the convolutional neural network that they learn local features, the Fourier features are global. And the second is, so you can see from here to here, we can intentionally truncate some high frequency modes that is not very helpful for operator learning. So this is the Navier-Stokes example. This is the Navier-Stokes. This is the initial velocity field on fluid, and you can see at the beginning there is a lot of high frequency modes on the velocity field, and by doing this frequency truncation, your solution is actually very smooth. And this is the figures from the new Fourier neural operator. So first, so then they mentioned in this journal paper, they mentioned there are two problems with the Fourier neural operator. So the first is, it cannot handle if the functions are defined, the input functions and the output functions are defined on two different domains. So their first proposal is to define a product space of the input and the output. So in this Navier-Stokes equation, basically it just append another dimension into the input function, and the other modifications they made to FNO is using RNN that to capture the temporal information. I guess for this, I'm not very agree on their statements. So if you look at first of all, if you look at the experiments on the original Fourier neural operator, so this one, so you don't have to propose to another product space to handle the temporal information. If you look at their experiment, the experiment of FNO, they have FNO 2D and the FNO 3D. And for the FNO 3D method, they handle the temporal information into a convolutional kernel. And actually, the second modification of DFNO plus is not new. If you look at the FNO paper very carefully, the FNO 2D do the exact same thing. They use the RNN to encode the temporal information. So I'm not very agree with the DFNO plus of this paper.
One second, Shiguo. What do they mean by expanding the output space with additional time t? So this is a case where the output space is larger than the input space.
This is your initial viscosity is only depending on x and y, but your solution will have x1, y, and t. This
How do they make FNO work on this case? Oh, this is the case. This is the problem, and the methods are the different strategies to address this problem.
Yeah, right.
Okay, this method 1 is straightforward. So method 2. How about method 2?
The method 2 is using actually, if you have a solution like this is time t, and they're using RNN to capture those temporal information.
So that means, okay, they still learn a mapping from Vx to Ux, but at some delta t, and then from Ux delta t to Ux 2 delta t, they use RNN.
Yeah.
And keep going.
Yeah.
Okay. You say you disagree with their.
No, I don't agree with them, because this, especially the method 2, is exactly the FNO 2D in the original FNO experiment.
Oh, okay. So
yeah,
they claim this is their own contribution.
Yeah.
Yeah.
Yeah, their contribution as DFNO, but I don't think this is something original. And for the method 1, I think it's trivial, because in the original FNO paper, the FNO 3D actually using a convolutional kernel. You can think of it as a 100 channel kernel to handle this temporal information. It's much efficient than this one, I think.
Well, what's the meaning? Using 100 channel, what does those channel, what do these channels represent?
Temporal information. It's a still do you can think that we do the convolution over image, but now the image maybe have 100 channels for each time steps. So you still have a 2D representations.
And each channel, the output of each channel represent a different time or different time step or whatever.
Different time step.
Oh, okay.
Yeah. If you use a convolutional kernel on this huge tensor, then we will still have a feature map that is 2D, right? So that's FNO 3D.
Yeah, but if you just use convolutional kernel, the relationship between those channels are ignored, right? How do they capture the dependency between the time steps?
But you can use multiple channels. You don't have to use one convolutional kernel. So you can use 100, 200 convolutional kernels.
Yeah, I mean, what you said is that, okay, if I use 200 channels, that means the output at each channel represent the solution field at particular time point, time step.
Probably, yeah.
But those fields at different time steps, they are dependent on each other, right? How do you model that if you only use convolution kernel with multiple channels?
If you use multiple channel kernels, I don't know how the convolutional will capture the temporal dependency explicitly, because if you have 3 convolutional kernels, then you have 3 feature maps, and then you expand it, and then we will have another weights. So it's not explicit representation.
But if you do
the-
this every step, it might be because every time you do some nonlinear transformation, you do the convolution again. I don't know. It might be possible. I don't know. Yeah, because the time steps they have an order, right?
Yeah.
They have some like one by one dependency on each other. Okay.
It's like the conventional convolutional network. It's hard to explain where the classification comes from, which the RGB channel. So it's less explanations. Another modification is that, so as we have discussed before, so what if you have irregular input space and that has a hole on it, and that the RGFNO will solve this problem for by first make a bound and they extend those boundary conditions and make it a proper defined rectangular lattice meshed input space. Basically, that's GFNO does.
Okay.
Yeah. And now the summary, the attributes of the DeepNet and FNO. The first, the D, the input space. DeepNet is arbitrary, and the FNO has to be the same. The discretizations of the output functions of U, well, DeepNet doesn't have to be, and the FNO has to be, because we need to do the fast Fourier transform on the output space. And the meshes, it could be arbitrary meshes, and the FNO has to be grid. Well, I agree with them, because FNO, if you do the FFT, you have to be on evenly gridded space. But I think for the neural operator, there is another way called GNO, graph neural operator, that's designed to solve the irregular mesh problem. The predict location, FNO assume that the predictions is the same as the grid points, and DeepNet can be arbitrary, and DeepNet doesn't require a full field observation data, but FNO does. I think if you want the DeepNet to work very well, you have to. So more training example is more better, right? So that's not a requirement, but that cannot make sure that DeepNet performs very well. And for discontinuous functions, DeepNet can handle, but FNO is not sure. That's their comparison.
Hi,
And,
Shibo.
Yeah.
Yeah. I have one question here.
Mhm.
So, what does the mesh describe? I mean, what kind of structure does mesh describe here?
Oh yeah, so that's a good question. Actually, so for PDE, to solving a PDE, we need to the golden standard of solving PDE is numerical solvers. But you need to, in order to use the numerical solvers, you need to tell the numerical solver where your function needs to be evaluated. We call it mesh. Basically, you need to put a mesh on the input function space, and the numerical solver will solve each point iteratively. That's a very accurate and but very slow. And if you are on a very coarse mesh, the numerical solver is very fast but erroneous. But if you are solving the PDE on a very fine mesh, it's like 100 by 100. It is very accurate, but it's extremely slow.
Yeah, I see.
Yeah, and this is the mesh, and this is the regular mesh we used for PDE solvers, and the FNO can only handle this kind of mesh. But what if you have a very weird solver, or you have a problem that you have irregular meshes? For example, if your a defined mesh is like this is another mesh, right? Then FNO cannot solve a mesh like this, because you need to, in order to proper operate the Fourier transform, you need to the mesh look like this, not like this. But there, the same group of FNO, they also have another word called AGNO, basically using the graph neural network to handle these irregular meshes. And then the integration over the mesh will be like the message passing over the over the graph.
Thanks. Is that because FNO requires the grid instead of the arbitrary mesh? Is that because for the it involves the Fourier transformation?
Yes. Yeah. Exactly.
Okay.
Yeah. Exactly. Yeah. The problem is not because the theory part of FNO, because it needs proper perform the FFT. FFT requires that your space need to evenly discretized.
Yeah, I see. Thank you.
Yeah, if you develop some more fancy Fourier transform that can perform on this, then FNO can also handle this.
I got a question. I don't think this claim is right. So your FNO prediction is the discretized solution function at the field, right? But
Yeah.
even if you only sample a few of them, you can view the remaining predictions. You don't observe them. You just fit the observed one into the square loss. There won't be any.
No. What you cannot do that. You need to. Oh yeah. For the output space, yes. Yeah.
So what's
right.
the problem here? Like I can generate prediction over the whole 100 by 100 grid, but I only use 1,000 of them to fit the 1,000 observations.
But I think we have discussed before, if you have a numerical solver and you have a mesh, so in what kind of case that you only have, for example, the solutions at this point and at this point?
That's the problem of DeepNet. If you want to get the training data from some PDE or from some ODE, if you run numerical solver, it will give you the solution values at all the full mesh, right? At the whole grid. Why should we start a lot of values to construct training set? But then you brought up some example, like suppose you have some like input, but you just you have some like station, right? You only have some discrete stations. You can view their values as only a sparsely sampled output. That's fine. I mean, using FNO, that just means okay, your observation is sparse, but your prediction is dense. When you're training, you just fit your prediction to the sparsely observed data points.
Yeah, I agree. Yeah, I agree. But this is the opinion from the DeepNet people, not from the FNO people.
I mean, they're kind of emotional, but I just want to understand what's the real advantage and disadvantage for both methods. Like if you view it as a Bayesian way, right? We can consider, okay, I can predict like 100 by 100 solution values, but I can marginalize out all the unobserved ones. Just fit
Yeah, right.
just calculate likelihood for the 1,000 sparsely sampled ones. I can still do the training procedure. There won't be any issue.
Yeah, right. I agree. Yeah, any other questions about the general comparison about the DeepNet and FNO? And then I will move to the experiment part of there. Yeah, so the first, they actually conduct lots of experiments, like 16, but I only have maybe 4 to 5 in my slides. So the first one is the classic Burgers equation, and then they compare their pod DeepNet with they also like the conventional neural network. They also do the layers rescaling trick that they, which is here for Burgers equation. They compare the pod DeepNet, and this is DeepNet with normalization or without normalization.
What does it mean for normalization?
I think I kind of forgot what the normalization means here.
Is it like batch normalization or not?
I think so, because they talk about the normalization with the same section as the rescaling. So it's like some implementation tricks.
Okay.
Yeah. Maybe they centralize the outputs. Then they will be the batch normalization, I think. And this is it's not the same experiment settings, but this is the results from the previous Fourier paper. And so in this, they compare the Fourier. You can see that their pod DeepNet is better than the FNO, but in previous FNO paper, they improved the DeepNet by
The PodNet feels slightly worse, right? 1.94.
Yeah. I think for Burgers equation, their performance is compatible. It's
So what does S mean? S is the sample rate of the input function, or whatever.
where is S?
The second table. The first.
It's the origin. This is the mesh size. This is Burgers is a spatial temporal function, right?
Okay, so the 256 by 256, something like that.
Yeah, I think it's 206 by 206.
Okay. What's the input dimension? How many data points? How many input function values did they feed to DeepNet or FNO?
For the left table.
From right table.
I kind of forgot. This is was the last presentation.
Okay.
Yeah. And they also do the Darcy problem, and then you can see that this is the pod DeepNet, and this is the best is the FNO with normalization. And they also improved that, and this is the previous. This is the results provided by FNO, and they improved DeepNet by 4 times.
Also, the POD net is much better than dipole net. Okay.
Yeah. And then I think the comparison is kind of, I don't know. So they also, this is the Darcy problem on a regular input space. Now they modify the input space of the Darcy problem as a star with a hole, or rectangular with this rod here. And this is, in this domain, FNO cannot be, it cannot handle this kind of input domain. Then they implement the DFNO or GFNO, and you can see that this is their implementation. And this pod dipole net is, I think it's at least 5 or 6 times better than the DGFNO, which is also their proposed method. Another is they also study the aerodynamics of a high-speed aerodynamics involve the linear instability waves. For here, they compare the FNO and the dipole net. This is the loss, training and the testing loss. And you can see that the test loss of the dipole net is 10 times better than the FNO. But the relative error, I think that it's not that significant. The dipole net is here, and it's here. It's also compatible, I think.
So the test loss, oh, okay, test loss is the solid line.
Yeah.
So is there, the best is the, okay, so the best case is the dipole net rather than pod dipole net.
Yeah, right.
Okay.
And they also do an experiment on a irregular space with a hole, which is
one thing, I need to confirm with you. So for this comparison, they have the same domain, right? They don't use any modification of the original.
No.
Okay.
This is a regular domain, but the study domain is a subdomain where the high linear the instability wave happens. So it's just the same domain. It's just a regular domain. And this is another is a velocity on a surface on an irregular domain, and I think this domain is irregular, but I don't know why they have the FNO results here. So you can see that dipole net with feature expansion, because the output functions has a lot of periodical features, and they do the feature expansion, and you can see that dipole net, by doing the feature, first of all, by doing the feature expansion is better than not doing the feature expansion. And the second, they want to prove the DFNO actually works, and because the vanilla FNO does not work, but the DFNO is still worse than the dipole net with feature expansion. And they also do the Navier-Stokes equations experiment, and well, I don't know why this results really upside the dipole net people, because in the original FNO paper, they didn't compare the dipole net on the Navier-Stokes equations. But I don't know why they said the comparison is not fair on the Navier-Stokes. But they actually conduct a Navier-Stokes comparison, that the pod DeepNet is achieved the best results. It's better than the FNO with normalization. And yeah, actually, they also report the results of DeepNet, I think, which takes a lot of time because DeepNet on Navier-Stokes is a very time-consuming experiment.
Oh, that might be the reason why the FNO doesn't compare with DeepNet in their paper.
Yeah, right. Because you have to expand the training each pair of functions into number of where the output function is evaluated, right? So for example, the Navier-Stokes has 100 by 100 by 200, which we will eventually have 2 million training examples for each pair of functions. So it is very time consuming.
Did they disclose how many training examples they use to train DeepNet?
For this one?
Yeah, for Navier-Stokes.
No, they don't. I didn't find any. The number of training examples. I don't think that maybe, but there isn't any very specific experiment set up in this draft.
Okay.
So I didn't find how many training examples they used.
And also, did their result match the results reported by FNO paper? Looks like does not match very much.
I think the recasty, so they used the recasty as 0.01, which is this column.
Okay, so 0.0086. So is 0.86%. 0.86% is actually much better than PODNet.
Yeah, I don't know.
Yeah, there's a huge difference here. I don't know how they
Yeah. Then the last is so the neural operator.
So maybe they have used different forcing term F.
I don't know. What's the F represent here?
F, I mean here they define F is a combination of sine and cosine, right? Well, I don't know what's in the FNO paper how they define the forcing term.
Okay, maybe.
Okay.
Yeah. And after all of this, and the neural operator people also proposed the physical informed neural operator, which is also exactly the same as the physical informed DeepNet and the PNN. So basically, they also claim that they can achieve 0 training example by forcing the physical loss. So this is the previous data loss, and they defined a PDE loss, which is enforcing by a physical law restriction, and this
Boundary.
The boundary conditions, because this is G here. Well, nothing else. Yeah, the very interesting about this paper is they kind of split this one into 2 contributions and propose another framework they called a pre-trained solution operator, and they fine-tune the PDE loss, which I think is is really, really trivial and unnecessary. And during the pre-train, they use the data loss. And during the test optimization, they use the PDE loss. And you can also use the PDE loss during the pre-training. And you can also include the data loss into the test time optimization, which I think this is very trivial and then unnecessary. And like the meta learning we have already seen, they also defined a very weird loss called the operator loss, which is enforced during the test time optimization. The learn operator is not deviate from the pre-trained operator too much.
So during the test time, they're gonna optimize again?
Yeah.
Optimize for what? So
For
during the
PDE, the physical law.
I don't know what's the meaning here. So during the test, they have tested on PD with different parameters or whatever.
It might be sample another set of calculation examples, or you can also include more training examples.
But once they have trained this offline, why do they train again during the test?
They just want to. I think they just want to make more contributions, as more contributions as possible. I think this procedure is totally unnecessary. They want to, then during the experiment, they claim that this kind of framework can also be used as a transfer learning, which is making no sense to me. So basically, you can train on some roughly pre-train on some pair of functions, and then you have another functions. You can use the pre-trained model, and then fine-tune it with no training example or very few data examples.
Okay.
I think this is very trivial. There isn't much strong motivation behind this, I think. They also do the Darcy flow. They also FNO physical informed FNO is also much better than DeepNet on the Darcy flow. And yeah, this is the answer. This is their experiments. This is just for model fitting accuracy, and this is like the two-step training, pre-train and pre-train and the fine-tune. And after training, they can include, this is the number extra data samples and extra calculation samples used. And you can see that actually by incorporating more training example, calculation examples, the solution error is smaller, which is obvious, I think. And this comparison is totally unfair. They train the PDE, not PDE, DeepNet, pins. I'm sorry, as for here, it's use pins, and they're physical informed, and by not incorporating any more training examples, it performs better than pins. Incorporating more and more, and I don't think what they want to show here is stay the same. And they say that the PA it is 20 times accurate than 25 times speed up than PN. I think this experiment is problematic. And then the last one, why they proposed those two-phase training, because they want to incorporate the transfer learning into their Pinot work, and you can transfer those solutions across different Reynolds numbers. And this is the
Okay, so they might train their functional operator, their neural operator at Reynolds number 400, and then they use them to do the fine tuning to train the Reynolds number 500.
Yeah.
Oh,
This is to train the Reynolds numbers, and by training on these Reynolds numbers, then you can fine tune on those Reynolds numbers. This is 0.
Okay.
Yeah. And that's all my today's presentation.
Okay, great, thanks. Any question?
Any questions?
Yeah, so firstly, thank you for the talk today. I learned from this presentation, and I still have some questions. So firstly, for the DeepNet, and also includes the pins and the neural operator. So because when you talk about the example, it always involves the derivative such as the PDE and ODE. Is there any other application that I mean those network can apply to? Could you give me some more example?
Apply to mean
Yeah, I mean
how the applications of DeepNet maybe?
No. Actually, I mean, so in the current, in the example, you have demonstrated it always, it can be PDE or ODE. It always involves the derivative. So is there any other problem? It can, yeah.
No. Only the physical informed operator learning that involve the physical information. But I think in the previous presentation, we talked about the neural operator, and then the neural operator it's a general functions to. It's a general framework that learns the mapping from functions to functions. You can think that the transformer is a function mapping from function to function, or the style transformation. Like if you have a photo and you want to transform that photo into the Picasso style, and that's another function to function. It's a general framework. But I think for the physical informed, they always involve some derivative because the physical system are involve a lot of integral and differentiation operations. That's the physical laws, define the physical laws of the environment.
Okay, I see. Thank you. And another question, another question is that so when you talk about the zero training data, so I remember for the input of the DeepNet, it have two kind of input. One is the UX, another is the Y. When you say the zero training data, do you mean we don't need Y to
we need Y. Yeah, we need Y. We need
what's the zero mean here? The training data.
I'm sorry. Can you say the last question again? What was the?
Yeah, when you talk about the zero training data, so what does that mean?
It means that you don't need to. You need to know where what is Y, but you don't need to know the ground truth of GUY. So basically, the GUY is always given by a numerical solver, which is very costly. But for simple physical system, if you know the dynamics, you just need incorporate the dynamics, the known dynamics into the training. You don't need to a numerical solver to generate the ground truth for you. You can just use the physical laws to produce a very good physical model.
I see. So it's kind of like that. You don't need the ground truth for the GUI.
Exactly. Yeah, right.
I see. Okay, thank you.
No problem. Any other questions? I can take one more. So it's a little bit over time.
Is it possible to use the DeepNet or its variants to approximate the operation of the Fourier transform?
I don't know. That sounds.
Or any other functional transform?
I don't know. It's open question. Yeah, probably. Yeah, if for Fourier transformation. Yeah, basically Fourier transformation is just integral over orthogonal function basis, right? So possibly.
I'm just curious about this problem.
Yeah, and also, yeah, but the experiment have shown for operator learning are still, I think, toy or simple problems, even though they are used in complicated physical system. But I think that it's not that. Still have a very restrict application domains. If it can apply to Fourier transform or other more general operators, I don't know. I'm not very sure about that. Maybe.
Okay, so in other words, so can it be used as a feature extractor for some other applications? Like after certain operations, we can transform the original function to some other space, and we can get some features that is useful for the downstream tasks.
Yeah, right. So I think that's a clear question for neural operator, because you can think that the neural operator leaves the original space, and after some complicated neural, the integral and local and the global operations. And I think that for the last layer, just do linear projections. Then the layer before Q, it can be used for downstream applications. But I think for DeepNet, since they model the input functions and the output functions independently, I don't know before the inner product those two features can used or for downstream application or not. I think it will be less informative than the latent vector that produced by the neural operator, right? That's my guess. Because in the trunk net, it's just lifting the inputs of the output functions to a high dimensional space.
Yeah, I don't know if the training or the parameter update would be easy if we use it as a feature extractor.
Yeah. Other questions?
Okay, I think if we have more questions, we can discuss about it offline. Okay.
Okay.
Thanks, Shipur.
Thank you.